Alright, welcome to take 2 of relearning kinematics. I filmed the whole thing on Zoom recordings and then it deleted it because we don't have that permission on our Schoology account. Yay. Anyways, for my video project, I will be going over kinematics. The purpose of this presentation will be to be revisiting the foundation of physics. It was the first unit we learned. It is the one that I'm most far removed from. I remember it being one of my favorite units, but I totally forget it at this point. It was over the summer, and I just genuinely don't remember it. I don't even have my notebook from that time, because I went through like 3 this year. So at this point, I just need to go over it completely because it is so important to everything we do in physics. Physics is the study of movement and all the things that objects do, and without knowing kinematics, you're kind of really set up in a bad place going on to future things in physics. So I really just need to go back, go over this unit, and make sure I understood it. So in that, I'm going to go over a couple concepts that I thought were essential when I looked at the EQs for this unit. And in that, I saw magnitude, vector versus scalar quantities, because those are so important when you go into future units and you have to identify, you're doing calculations and you don't know which kind of quantity you're looking at, and then you mess up the whole equation. And in vector versus scalar, you have displacement versus distance. That's also very important. Velocity and accelerations graphs. Since this unit, I have gotten to derivatives in calculus, and these graphs make a ton more sense than the trends that I just visually identified. I can finally actually understand what I'm looking at. And then overall, the kinematic equations, I kind of forgot them, and it's kind of important to just like memorize those. So first off is magnitude. This is kind of just like a basic concept of like numbers. When I did the EQs over the summer, I actually included that original definition that I had before ever taking physics. I had said that magnitude is the sum of the physical quantities that are being described. Essentially, it is the numerical value that represents the physical quantities. And while this sounds like a bunch of just words, it actually makes a lot of sense to me. If you look at the arrow right here, you see that it's going in this direction, but the magnitude is only the tail to the head. It doesn't matter the direction. It is just... Oops, sorry. So magnitude is like if you walk 4 miles east, it doesn't matter the east or that you walked or anything like that. All that matters is that 4, and your unit is miles. So I mean, you'll probably include the miles, but all that matters right there is that 4, that number right there. That is the important part in the magnitude. So I just find like super interesting. Vector versus scalar, like I said, this is super important when you're first starting physics to identify the difference between these two. Vector takes into account magnitude and direction versus scalar, it only takes into account magnitude. So scalar only thinks about that number, it does not care about the direction. It doesn't care if it's up, down, left, or right, who cares? Vector, it does. So a vector quantity could be velocity, displacement, force, acceleration, momentum, while scalar takes into account momentum. It takes into account only magnitude, so it would be like speed, mass, temperature, distance, time. So in identifying the difference between these two, you can look at a problem and see which kind of equation am I going to need to use. Scalar quantities are a lot more simple. There's a lot less things to think about. Is just thinking about magnitude versus vector. It's taking into account a little bit more, which becomes very complicated when you're going to future units like momentum, which is where I got very confused because I forgot this basic concept of just vector. It's important to know that magnitude can change the positive and negative sign of a value because you're thinking if it goes down, that is a negative. And that's so complicated to wrap your mind around, that negative momentum doesn't mean there's a loss of momentum. It could just be meaning that there's momentum going downwards. Anyways, so vector quantities in practice, this is what I'm talking about, and the direction is everything. So I have this example of a frog hopping with initial negative velocity. So he's hopping in a negative velocity. This doesn't mean he's losing velocity. It just means the value of his velocity is negative. He spots a pond and begins to accelerate positively. How will his final velocity be affected? So when looking at this situation, how I defined it, there's a couple different ways you could, but how I defined it was that he had an initial negative velocity. He's moving in a negative direction. Maybe he's moving west, maybe he's moving south. And then he begins to speed up positively, which means he's going increasingly into that negative direction, which means his final velocity is going to be a greater negative than his initial velocity. And while that might not make sense because it's increasing positively, and adding a positive to the negative should cancel it out, it's actually that because he's moving more in that negative direction, it's just going to be more negative. He's going faster, but because it's in that negative direction, it's going to be a greater negative. So going back to these vector versus scalar, displacement is the vector value, while distance is the scalar. So displacement only takes into account your net movement. So if you move 10 meters up and 10 meters down, you've moved nowhere. And distance would say it doesn't matter what direction you moved in. If you moved 50 meters this way and 60 meters that way, you moved 110 meters. So in this problem, a frog hops 10 feet east, 5 feet north, 10 feet west, and 2 feet south. What was the frog's displacement in his journey? You would think about that canceling out versus in direction. So if he's going 10 feet east and 10 feet west, that cancels out. Those two things are gone. Because he's going back to that place he started. You got to think about like a number line. If you go all the way to the end and then come all the way back to the start, you've moved nowhere at all. Versus the 2 feet north and 5 feet north and 2 feet south, that cancels out 2 feet from the north because he moved back 2 feet. So he only moved 3 feet north in his total displacement. Versus the distance, you would add all of like quantities together. He would have ended up moving 20 feet and then 27 feet total. So then in the position velocity acceleration graphs, these are all based on derivatives. I don't want to go too much into it because we're not supposed to go, we're not doing a lot of calculus in this class, but essentially each of these are derivatives of one another. A position, you would take the derivative of a position graph to find the velocity graph, and you would take the derivative of a velocity graph to find an acceleration graph. So you would think like the position graph would have a function of like 3x squared, the velocity graph would have an equation of 6x, and then the acceleration graph would have a formula of like 6. Then we have our kinematic equations. These are the foundation of everything that we do. When you go back to it, all I ever think of is force equals mass times acceleration. There's important equations that you just have to memorize. And these, you might not have to memorize all of them, but you do have to memorize how they relate and what they mean. And in them, change in x is displacement, v naught is initial velocity, and v is final velocity. This is going to conclude my video for right now, because I think the most important part in kinematics is just knowing how these equations relate, and how all of the things that I've mentioned in this presentation come together to be the unit we've discussed.